Welcome to our discussion on the product and quotient rules. These are two rules that you guys are going to use over and over and over again to take derivatives. They're going to be very handy, and it's going to be very important for you to basically memorize the formulas and how to use them. They're pretty easy to remember. Now, for those of you that are stopping with Calc 1 and aren't going on to Calc 2 and further studies of mathematics, you probably don't need to spend a lot of brain power trying to understand why the product and quotient rules work. I am going to spend some time here going through the proofs of both, so those of you that care to understand how and why the rules work, this will be helpful. For the rest of you, you probably just want to know, give me the formulas and let me go about my business. And for that mindset, really, this is all you care about. Is the table of formulas that basically sum up everything that we've learned so far. We know everything up to the last two already. We know the derivative of a constant, the derivative of x to a power. We know the derivative of e to the x. In fact, we almost kind of know the derivative of a to the x, which we'll see that pretty soon. We know the derivative of a constant times a function, and then we know how to add and subtract functions and take their derivatives. And now we're going to learn how to do the product and quotient of functions. Okay, let's start with the product rule. And unfortunately, the product rule doesn't work the way we would wish it would. We can't take the derivative of a product and make it the product of the derivatives, right? It's not like limits. So this is really important that you realize that that is not true. And you can see it very clearly from a simple example. Take f of x equals x, g of x equals x squared. The power rule tells us that the derivative of f is 1, the derivative of g is 2x, right? But the derivative of f times g, which of course is x cubed, is 3x squared, which is not the product of 1 times 2x, which is 2x, right? They're way off. They're not even close. So the derivative of the product is not the same thing as the product of the derivatives, unfortunately. So there has to be a different way. And it really helps to think about this geometrically. Okay, so the white square represents u times v. Now, in order for this geometry to make sense in your minds, we're going to start off by assuming that u is the f of x function, v is the g of x function, and both of those functions are positive and differentiable functions. Differentiable, no duh, but we're going to assume they're positive. That's a big assumption to make, because not all derivatives so not all functions are positive. But we'll see later that we don't need that assumption. We're just doing it now so that the picture makes sense in our mind. So then, of course, if we have u times v, we get that white square. Well, this distance here is how much the v function is changing. That's the change in v, right? And then this distance here is how much the u function is changing. That's the change in u. And then very clearly, the blue, right? Here's v times a change in u. That's v du, right? And here's u dv, right? Because this is the length of u times the change in v. And the little green square is the change in u times the change in v. So geometrically speaking, that's what this picture represents. Okay, so if x changes by a certain amount, so we let x change a little bit, then the corresponding changes in u and v are going to be the change in u, right, and the change in v. And the change in u is just going to be f of x plus that little delta x minus f of x, right? It's the new value of the function. So x went from 1 to 1.1. So now we're going to evaluate the function at 1.1, which is 1 plus the change being the 0.1. Right, so you can think of this as, let's use something besides 1 and 1.1. Let's say x goes from 3 to 3.01, right? So this is 3.01. You take the derivative of 3.01, sorry, you take the function evaluated at 3.01 and subtract the function just evaluated at 3, and that's how much you've changed, right? That's the change in the output. And the same thing would be over here for whatever the change in x was, right? Wherever we start, it would be g of 3.01 minus g of 3, and that's how much the g function of has changed for a 0.01 change. But now we just think of, delta x as being any small change in x. So then, by kind of substitution, the value of the product of u plus change in u times v plus change in v can be interpreted as the area of the large rectangle in our figure, provided that u and v happen to be positive, right? That when I said the large rectangle, I mean the whole thing, all three colors plus the white bit, right? Because if you FOIL this out, you get uv, right? U times v plus u delta v plus v delta u plus delta v delta u, and that's all of those four pieces put together. Okay, so the u plus its change times the v plus its change gives you all that area. So all of that area represents the overall change. So therefore, the change in the area of this rectangle is the change in u times v, right? Because the original product was just u times v. Now we're going to let both of them change a little bit, so that's why it's u plus delta u times v plus delta v. That's the change. Subtracting away the original uv piece, and that's why we're left with those three colored pieces, right? The blue piece, the green piece, and the, I don't know, orangish piece. Those three pieces are the actual increase, right? The increase in the product of uv. It went from this size up to that big size, and that's the increase in the size. The sum of those three shaded areas. Okay, if we divide everything by the change in x, so remind yourself, we're taking this big thing and we're dividing by the change in x. So we now have the change in uv over the change in x equals u change in v over change in x, v change in u over change in x, and then change in u, change in v over change in x. And this last piece, you could have put it under either of them, right? It could have been change in v times change in u over change in x. Doesn't really matter. Okay, now if we let the change in x go to 0, we get the derivative by definition, right? If you let that delta x go to 0, that's what the definition is. It's the limit as h goes to 0, right? And h going to 0, same thing as delta x going to 0. So on the left-hand side, we have the derivative of the product of uv equals the limit as delta x goes to 0 of all of this stuff, right? By substitution, we're just doing these two things. This piece here, that piece there. And now we can kind of figure out what this stuff is. Well, in this, we're taking a change in v, right? We're basically, we're taking the limit now and we're putting it into each piece. This is a constant times this stuff. Remember, because if we're taking a limit as delta x changes, there's no delta x in this, so it doesn't change at all, so it's a constant. So with the limit laws, it comes outside the limit, and then you have the limit of change in v over change in x. Same thing here. The v is a constant, so it comes out, right? And then the last one, we're taking the limit as x goes, change in x goes to 0 of all of this stuff, this piece times this piece. There's some change going on with both of them, so we have to think about the limit of both of them. Okay, well, this, by definition, right, is just the change in v with respect to x. So that's the derivative of v with respect to x. This one here is how much u is changing with respect to x. That's the derivative of u with respect to x. This one here, this piece is how much v is changing with respect to x. That's the change in v with respect to x. But this piece here is saying take the change in u, right, and look at what happens to it when the change in x goes to 0. Well, you'll notice that as delta u goes to 0 just as delta x goes to 0, because if the change in x goes down to nothing, then from the previous picture the change in u isn't going to be anything. So that's why that becomes 0. It's basically the same thing as just looking at the change in x, and that makes this thing 0, which of course gets rid of that, and we now have our function for the product. The derivative of a product is kind of the sum of these weird things, right? The derivative of u times v is u times the derivative of v plus v times the derivative of u. Now, I know we originally assumed that all quantities were positive to make the geometry make sense, so that picture would make sense. But the algebra was valid whether u, delta v are positive or negative. All those previous steps, positive and negative doesn't matter. So we've actually proven that this thing works for all functions. So now we have our first rule, and a very important one, that the derivative of a product is the first times the derivative of the second plus the second times the derivative of the first. And since it's a plus, it can go either way, right? Some textbooks and some people say, well, it's the derivative of the second times the first plus the first times the derivative of the second. Well, isn't that the same thing? Right? It's like a plus b versus b plus a. Just make sure that, to help you remember these things, think of them in two pieces. Okay? There's the yellow piece and there's the green piece. And what do they have in common? In both of them, they have one of the original functions, right? And then they have the derivative of the other function, right? So you've got two functions, f and g. You take f times the derivative of g, and then you also take g times the derivative of f, and you add those two things together. It doesn't matter which one comes first because a plus b is the same thing as b plus a. Okay? That is the product rule. Here are some examples. We can blow through these and see how it works. We're taking the derivative of x times e to the x. So there's one function, and there's the other function. So that's my f times g, right? So here's my f times the derivative of g. And then here's my g times the derivative of f. And then at the end it's just a matter of some algebra to kind of clean it up, i.e. they factored out the e to the x. So now if we want to try and do the second derivative, we're just taking the derivative of this new product. This is my f, this is my g, right? This thing times that thing. And then you repeat the process. And we could do this all day long. We can see that if we do it to the third, it becomes x plus 3. If we do it to the fourth, it's x plus 4. And of course, if we do it to the nth, we get x plus n. You'll start to see that whenever we're taking derivatives that involve e to the x, patterns seem to erupt. Okay, the quotient rule. This one's a little trickier than the product rule as far as the proof. But again, most of you don't care. Those of you that do, please buckle in, pay attention. It's a little tricky, but it's not too bad. All right, we start off with relatively the same idea. If x, u, and v change by the little amounts delta x, delta u, and delta v, then the corresponding change in the quotient u over v is written suchly. Right? This is just saying how much is u over v changing. This is the change in u over v. Well, it's going to equal u plus a little bit of a change in u over v plus a little change in v minus where it started originally. Right? So think about something as simple as 2/3 changing by 2.5 over 3.1. So 0.5 is my change in u, 2 was my original u, right? 3 was my v, 0.1 was my change in v, and I take that and subtract the 2/3, and it tells me how much that fraction has changed. It's gone from 2/3 up to 2.5 over 3.1. If you do the math, which is some ugly math, you'll get how much that fraction has increased in this case. Remember, it doesn't always have to be a positive increase, but it just makes it easier for our brains to understand it. Okay, well, if we want to write this as one big old fraction, we got to do a common denominator, which means multiplying this thing top and bottom, on the bottom by v, right? Top and bottom, v over v, and then this thing top and bottom by v plus delta v. And that's where we get this. U plus delta u times v minus u times v plus delta v all over the product of those two things. Do the foiling, right? You get that's a v, uv plus v delta u minus uv, right here, and then minus u delta v. The uv and the minus uv cancel, and you're left with v du minus u dv, right? V du minus u dv. And then the bottom doesn't change at all. Alright, well, this is where we are on the last slide. So now, instead of thinking of it as delta, right, that's the same thing as the derivative with respect to x. So the derivative of this is just going to be the limit as delta x goes to 0 of this original thing over the change in x, right? So the change in this over the change in x. Well, the change in this thing was this piece here. So it's going to be that piece over the change in x. But when you divide a fraction by the change in x, you're either dividing the pieces of the top by it or just one time in the bottom. And what we did algebraically, it was more advantageous to put it in the top. So there's this piece over change in x, this piece over change in x. You can see that that would be the same thing as this whole thing over the change in x, which would put it on the bottom, which would put it down here, right? All we did was algebraically put it into the fraction. Now, as delta x goes to 0, we can see that delta v goes to 0. Also, because v equals g of x is differentiable and therefore continuous. Thus, using the limits, we get this stuff, which is where we were right here. And then we can now bring these limits inside of all of these, right? We can bring it inside v, we can bring it inside u. We're basically taking those constants out because they're not changing. Same thing on the bottom. We're taking the limit of a quotient, the same thing as the quotient of the limits, right? So we're bringing this one inside. Again, we can pull this constant out. On the top, this piece here is just the derivative of u with respect to x. This piece here is the derivative of v with respect to x. And on the bottom, as x goes to 0, this goes to 0, and we just get v times v for v squared. And ta-da, we have the quotient rule. If we're taking the derivative of a quotient, it's very similar to the product rule, right? Look at the top. We've got two pieces again, a yellow piece and a green piece. And in both of those pieces, we have one of the original functions, right? And then the derivative of the other piece. But because there's a minus sign instead of a plus sign, order does matter here, right? A minus B is not the same thing as B minus A. So now we have to really pay attention that when we have these two pieces, it's the bottom times the derivative of the top minus the top times the derivative of the bottom, and then all over the bottom squared. So the bottom stays on the bottom, it just gets squared. So that kind of helps you with that. So again, bottom times derivative of the top minus top times derivative of the bottom all over the bottom squared. And that's the quotient rule. Here's an example of it. You can see that the math gets kind of, I don't know, tedious. It's not difficult. It's just tedious because you have to square things, and then you have to take you have to take products of things, and then you have to take the difference of them, right? So you have to FOIL out the left, you have to FOIL out the right, then you have to subtract the right from the left, which means you have to combine all your like terms, and then you finally have a big old polynomial over the bottom. Possibly the top would factor, and then you would reduce it further with the bottom. So it can get to be a nightmare algebraically speaking, but it's a pretty easy technique as far as the quotient rule is concerned. And as we saw at the beginning, here are all of the rules put together in one nice little slide for us. That's what most of you care about. There it is, right? Bottom times derivative of the top minus top times derivative of bottom all over bottom squared. And here's this one, right? One of them times the derivative of the other plus the vice versa, right? First times derivative of the second plus second times derivative of the first is normally how I tried to memorize it as a student. All right, guys, that is the product and quotient rule.